The Medusa Galaxy, also known as NGC 4194, is an intriguing and extraordinary cosmic structure located approximately 130 million light-years away in the constellation Ursa Major. It is classified as a merging galaxy, born from the collision of two previously independent galaxies, a process that has shaped its distinct and chaotic appearance. The Medusa moniker comes from the bright streamers of gas and stars that resemble the mythological character's snake-like hair, highlighting the dynamic processes at play in this galactic system. The Medusa system provides a wealth of scientific interest due to its rich interplay of stellar formation, gas dynamics, and the gravitational effects resulting from the galactic merger. The galactic collision that gave rise to the Jellyfish Galaxy is a prime example of how the universe is an ever-changing environment, driven by the relentless force of gravity. During this cataclysmic encounter, stars from the progenitor galaxies mostly passed by each other without colliding, as the distance between individual stars is vast on galactic scales. However, the massive clouds of gas within the two galaxies did interact, leading to intense bursts of star formation, a phenomenon astronomers refer to as a starburst. These starbursts are most visible in the core region of the structure, where dense molecular gas is compressed to form massive clusters of stars. Observing these starburst regions allows researchers to gain insight into the process of star formation under extreme conditions. The tangled morphology of the cosmic Medusa is not limited to its starburst core. One of its most notable features is the extended tidal tail, a stream of stars and gas ejected into intergalactic space due to the gravitational forces during the merger. These tidal tails serve as a direct record of the interaction, helping astronomers reconstruct the history of the collision. The tail also contains young stars, whose formation was likely triggered by the compression of gas in these outlying regions. The study of such features provides a unique opportunity to explore the mechanisms behind galactic evolution and the role of interactions in shaping the universe's structure. The unique environment of this stellar hydra allows for the study of feedback processes, where newly formed stars influence their surroundings. Massive stars emit copious amounts of ultraviolet radiation and powerful stellar winds, which heat and ionize the surrounding gas. In extreme cases, supernova explosions from these stars further enrich the interstellar medium with heavy elements and drive gas outflows that can escape the galaxy's gravitational pull. Observing these processes in the Medusa's environment helps scientists understand how galaxies regulate their growth and evolution over cosmic timescales. Furthermore, the chaotic nature of the nebular Gorgon is an ideal laboratory for studying the interstellar medium. The collision of the progenitor galaxies has created a turbulent and dynamic environment where gas exists in a wide range of temperatures and densities. Researchers can observe cold molecular gas, the raw material for star formation, as well as hot ionized gas that glows brightly in X-rays. The interactions between these phases of gas shed light on the complex physics that governs the interstellar medium and the role of turbulence in driving star formation. The study of the Serpentine galaxy extends beyond its immediate surroundings. Like other merging systems, it is believed that the Medusa will eventually evolve into a more stable elliptical galaxy, a process that takes billions of years. This transformation provides a glimpse into the future of galactic evolution and helps astronomers piece together the sequence of events that shape the observable universe. Additionally, merging systems like this one are thought to play a crucial role in the growth of supermassive black holes at the centers of galaxies. The Medusa galaxy's active core suggests the presence of such a black hole, which is likely accreting material from the surrounding gas, generating immense amounts of energy in the process. Advanced observational techniques have allowed astronomers to delve deeper into the anatomy of this galactic siren. Instruments aboard space telescopes like Hubble and Chandra, as well as ground-based observatories equipped with adaptive optics, have provided high-resolution images and spectral data of the system. These observations reveal not only the intricate structure of the galaxy but also the chemical composition of its stars and gas. By studying the elemental abundances in the Medusa stars, researchers can trace the history of star formation and chemical enrichment, offering clues about the conditions in the universe during different epochs. In addition to its scientific significance, the radiant chimera serves as a visual testament to the beauty and complexity of the cosmos. Its vibrant colors, ranging from the deep red glow of hydrogen gas to the brilliant blue of young star clusters, offer a striking contrast that captivates astronomers and enthusiasts alike. These colors are not merely aesthetic, they provide valuable information about the physical processes within the galaxy. For instance, the red emission from hydrogen gas marks regions of active star formation, while the blue light from young stars indicates their relatively recent birth. The Medusa's story is not an isolated one. Galaxies like the stellar vortex are found throughout the universe, and their study contributes to our broader understanding of cosmic evolution. Collisions and mergers are common in the history of galaxies, including our own Milky Way, which is on a collision course with the Andromeda Galaxy. By studying systems like the Medusa, scientists can predict the outcomes of such interactions and better understand the long-term evolution of galactic systems. The scientific investigation of the celestial hydra is an ongoing endeavor. As new telescopes and instruments are developed, astronomers will continue to unravel its mysteries, from the detailed mechanisms of star formation to the fate of its tidal tails. The insights gained from this galaxy and others like it are not just about understanding distant objects, they also shed light on the processes that have shaped our own cosmic neighborhood and the universe as a whole. The Medusa galaxy stands as a reminder of the dynamic and interconnected nature of the cosmos, a place where even the most chaotic and violent events give rise to beauty and new beginnings. The Medusa galaxy continues to provide an unparalleled perspective on the processes that govern the universe. Its chaotic structure, driven by the violent collision of two galaxies, acts as a cosmic laboratory where astronomers can observe the interplay of forces that shape galaxies over billions of years. The intricate dance of gravity, the dynamics of interstellar gas, and the cycle of star formation and destruction are all encapsulated within this remarkable system, making it a cornerstone for our understanding of cosmic evolution. One of the most striking aspects of the cosmic hydra is the diversity of star populations within it. The collision that created this galaxy triggered multiple waves of star formation, leading to the presence of stars of varying ages and metallicities. By analyzing the light emitted by these stars, astronomers can decipher the timeline of events that shaped the galaxy. Young, massive stars shine brightly in ultraviolet and blue light, while older, cooler stars emit red and infrared radiation. This combination of stellar populations allows researchers to reconstruct the galaxy's history and understand the long-term effects of galactic mergers. The tidal features of the nebular serpent are another area of intense scientific focus. These streams of stars and gas, stretching far beyond the main body of the galaxy, are evidence of the gravitational forces at work during the merger. Observations of these tidal tails have revealed that they are not uniform but contain clumps of gas and stars, suggesting localized regions of star formation. These star-forming clumps are of particular interest because they represent an environment vastly different from the dense cores of galaxies, providing a unique opportunity to study how stars form under low-density conditions. In addition to its visual and structural features, the Jellyfish galaxy is a hub of intense activity at other wavelengths of light. Infrared observations reveal the presence of dust heated by young stars, while X-ray emissions point to hot gas and possible supernova remnants. These multi-wavelength observations are crucial for building a complete picture of the galaxy, as each wavelength provides unique information about the physical processes occurring within it. For example, infrared light can penetrate dust clouds to reveal hidden star-forming regions, while X-rays highlight the most energetic phenomena, such as black hole activity and supernova explosions. The central region of the radiant Gorgon is particularly fascinating due to the interplay between its active galactic nucleus, AGN, and the surrounding starburst activity. The AGN, powered by a supermassive black hole, emits enormous amounts of energy as it accretes matter. This energy output can have a profound impact on the galaxy, heating and expelling gas in a process known as feedback. Feedback is a critical mechanism in galaxy evolution, as it can regulate star formation by either triggering new bursts or quenching ongoing activity. Studying the medusa's AGN and its effects provides valuable insights into the role of supermassive black holes in shaping their host galaxies. Another compelling aspect of the galactic siren is its chemical complexity. The collision that created the galaxy mixed the gas and dust from the two progenitor galaxies, enriching the interstellar medium with a wide range of elements. Spectroscopic studies of the galaxy have revealed the presence of heavy elements like oxygen, carbon, and iron, which are the byproducts of previous generations of stars. These elements are essential for the formation of planets and life, making the medusa a key piece in understanding the cosmic cycle of matter. The study of the stellar chimera also sheds light on the larger-scale processes that govern the universe. Merging galaxies like this one are thought to play a significant role in the hierarchical formation of structure, where small systems combine to form larger ones. This process is not only important for individual galaxies but also for galaxy clusters and even the large-scale cosmic web. By studying systems like the medusa, astronomers can gain insights into how the universe's largest structures came to be. Despite its apparent chaos, the Medusa galaxy is a system in transition, slowly evolving toward a more stable state. As the remnants of the collision settle and the bursts of star formation subside, the galaxy is expected to take on a more elliptical shape. This transformation is a natural part of the life cycle of galaxies and offers a glimpse into the future of similar systems. Observing the Medusa at this stage provides a rare opportunity to study a galaxy in the midst of this transition, offering a snapshot of a process that typically spans billions of years. The celestial serpent also serves as a bridge between the past and future of the cosmos. By studying this galaxy, astronomers can not only learn about the conditions in the early universe but also make predictions about the fate of galaxies like our own Milky Way. The Milky Way's eventual merger with the Andromeda Galaxy is expected to produce a system similar to the Medusa, providing a direct connection between these distant cosmic events and our own place in the universe. As technology continues to advance, the Medusa Galaxy will remain a focal point for scientific exploration. Next-generation telescopes, such as the James Webb Space Telescope and upcoming ground-based observatories, promise to unveil even more details about this fascinating system. These instruments will allow astronomers to peer deeper into the galaxy, uncovering hidden structures and probing the physical processes at work with unprecedented precision. From its starburst core to its extended tidal tails, the Medusa Galaxy offers an endless array of mysteries waiting to be unraveled, ensuring its place as one of the most captivating and scientifically valuable objects in the universe. The Medusa Galaxy is a cosmic masterpiece, embodying the complexity and wonder of galactic evolution through its intricate features, dynamic processes, and ongoing transformations. Its chaotic state, caused by the colossal collision of two parent galaxies, has rendered it a perfect example of the interplay between destruction and creation on a universal scale. The aftermath of this collision is not just a spectacle for observation but a living laboratory that reveals critical insights into the forces that shape galaxies, stars, and the very fabric of the universe itself. One of the defining aspects of this galactic chimera is its starburst activity, which remains a primary focus for astronomers. The gravitational interaction between the colliding galaxies has funneled vast amounts of gas and dust into the core, igniting an extraordinary surge of star formation. These regions are dominated by young, massive stars that burn brightly and emit copious amounts of ultraviolet light, ionizing the surrounding gas and creating striking emission nebulae. Studying these starburst regions helps researchers understand the mechanics of star formation under extreme pressures and densities, shedding light on how such processes might have occurred in the early universe. The surrounding environment of the Jellyfish Galaxy is equally fascinating. Its extended tidal tails, stretching tens of thousands of light-years into intergalactic space, are composed of stars, gas, and dust ejected during the merger. These tidal structures are often home to their own isolated pockets of star formation, where the conditions differ significantly from those in the galaxy's core. These stellar nurseries in exile provide a unique opportunity to study how star formation occurs in low-density environments, offering a stark contrast to the intense starburst activity in the central regions. The chemical makeup of the nebular hydra is another cornerstone of its scientific significance. During the merger, the interstellar medium was enriched with elements forged in the cores of stars from the parent galaxies. These heavy elements, such as carbon, oxygen, and silicon, are essential for the formation of rocky planets and, ultimately, for the potential emergence of life. By analyzing the spectral signatures of these elements, astronomers can trace the galaxy's chemical evolution and better understand the cosmic processes that distribute the building blocks of life throughout the universe. The Medusa's active galactic nucleus, AGN, is another area of intense interest. The AGN, fueled by a supermassive black hole at the galaxy's center, emits tremendous amounts of energy as it accretes surrounding matter. This activity has profound implications for the galaxy as a whole. The energy output from the AGN can heat the surrounding gas, driving powerful winds that can either trigger or suppress star formation in a process known as AGN feedback. Understanding this feedback mechanism is crucial for unraveling the intricate relationship between supermassive black holes and their host galaxies, a relationship that plays a fundamental role in shaping the universe on both small and large scales. In addition to its AGN activity, the stellar serpent is a source of high-energy phenomena observable in X-rays and radio wavelengths. These emissions are often associated with supernova remnants, neutron stars, and black holes, all of which are abundant in such dynamic environments. By studying these high-energy processes, astronomers can gain insights into the end stages of stellar evolution and the role of extreme astrophysical events in shaping galaxies. The Medusa's chaotic yet mesmerizing structure also serves as a window into the future of our own galaxy. The Milky Way's eventual collision with the Andromeda Galaxy will likely produce a system similar to the Medusa, complete with tidal tails, a starburst phase, and an active galactic nucleus. By studying the Medusa, astronomers can make predictions about the sequence of events that will unfold during this future galactic merger and how it will ultimately shape the structure and composition of the resulting galaxy. Beyond its immediate scientific implications, the Medusa galaxy contributes to our broader understanding of the cosmic web, the large-scale structure of the universe. Galaxies like this one are not isolated entities but are influenced by their interactions with neighboring galaxies and the surrounding intergalactic medium. The tidal features of the Medusa provide evidence of these interactions, offering clues about the galaxy's past encounters and its place within the larger cosmic framework. The radiant Gorgon is also a reminder of the universe's inherent beauty, where even the most violent and chaotic events give rise to stunning visual phenomena. Its vivid colors, intricate patterns, and dynamic features captivate both scientists and the public, serving as a powerful tool for inspiring curiosity and engagement with astronomy. The galaxy's striking appearance is a testament to the artistry of nature, where complex physical processes converge to create something both scientifically valuable and aesthetically breathtaking. Looking ahead, the Medusa galaxy remains a prime target for future observations. Next-generation telescopes, such as the Vera Rubin Observatory and the Extremely Large Telescope, ELT, will provide unprecedented views of this enigmatic system. These advanced instruments will allow astronomers to probe deeper into the galaxy's core, resolve its tidal structures with greater clarity, and uncover new details about its interstellar medium, star-forming regions, and AGN activity. Such observations will not only enhance our understanding of the Medusa but also refine our models of galaxy formation and evolution on a universal scale. The continued study of the galactic siren promises to unlock even more secrets about the universe's history and its ongoing transformation. Its chaotic state, though fleeting in cosmic terms, offers a rare glimpse into the processes that have shaped galaxies throughout the cosmos. From its starburst regions to its tidal tails and active nucleus, the Medusa galaxy is a microcosm of the forces that govern the universe, making it an invaluable object of study and a source of endless fascination for scientists and enthusiasts alike. As we unravel its mysteries, the Medusa reminds us of the dynamic and interconnected nature of the cosmos, a place where even the most tumultuous events are part of a larger, harmonious tapestry. The Medusa galaxy captivates not only with its violent origins but also with its profound cosmic implications. Every aspect of this galactic masterpiece tells a story about the transformative forces that govern the universe. Its turbulent evolution reflects the power of galactic mergers, a phenomenon responsible for some of the most dramatic changes in the universe's history. The Medusa is not merely a relic of an ancient collision, it is alive with activity, radiating energy and evolving in real time. The beauty of the jellyfish galaxy lies in the interplay between chaos and order. Its tangled tidal tails, shimmering with young stars, tell a tale of destruction giving birth to creation. These tidal features stretch far beyond the main galaxy, like celestial tendrils weaving a connection between the Medusa and the vast intergalactic space. Observing these structures reveals how stars and gas can be ejected into the void, where they might seed future star formation in entirely new regions. This process, though seemingly chaotic, is a fundamental mechanism by which galaxies grow and interact with their surroundings. The active starburst regions of the nebular Gorgon are among its most striking features. These areas are like galactic nurseries, where intense gravitational forces compress gas and dust to form massive, luminous stars. These stars live fast and die young, ending their lives in spectacular supernova explosions. Each supernova injects energy and heavy elements into the surrounding medium, enriching it and preparing it for the next wave of star formation. The Medusa, therefore, is not just a snapshot of galactic activity, it is a continuous cycle of birth, death, and rebirth, demonstrating the interconnectedness of all cosmic processes. The central supermassive black hole in the stellar hydra adds another layer of complexity to this fascinating system. Its presence exerts a profound influence on the surrounding galaxy, creating a dynamic interplay between accreting matter and the energy it radiates outward. Jets of high-energy particles are launched from the black hole's poles, cutting through the galaxy and affecting the surrounding gas. These jets can trigger star formation in some regions while quenching it in others, acting as both a creator and destroyer within the galaxy's ecosystem. This duality mirrors the Medusa's mythological namesake, embodying both beauty and danger. The Serpentine galaxy's rich diversity of stellar populations offers a unique opportunity to study the life cycles of stars. From the blue, young stars in its active regions to the red giants and dying remnants in its outskirts, the Medusa encapsulates every stage of stellar evolution. These populations serve as cosmic time capsules, preserving information about the galaxy's past interactions and star formation history. By analyzing the light from these stars, astronomers can piece together the timeline of events that led to the Medusa's current state, providing a detailed record of its cosmic journey. What makes the radiant chimera even more fascinating is its role as a bridge between different epochs of cosmic history. The conditions within the Medusa resemble those found in the early universe, where frequent mergers and interactions drove rapid star formation. Studying this galaxy allows astronomers to step back in time and understand how similar processes might have shaped the first galaxies. At the same time, the Medusa offers a glimpse into the future, as it provides a model for what might happen when galaxies like the Milky Way and Andromeda eventually collide. The Medusa's turbulent nature also makes it an excellent testbed for studying the physics of interstellar gas. The merger has created a chaotic environment where gas exists in various states, from cold molecular clouds to hot ionized regions. These different phases of gas interact with each other, creating turbulence that influences star formation. Understanding how turbulence shapes the interstellar medium is crucial for explaining why stars form where they do, and the Medusa provides a unique opportunity to study this process in detail. But the story of the galactic siren is not confined to its internal dynamics. It is also a key player in the larger cosmic web, the vast network of galaxies and dark matter that spans the universe. The medusa's interactions with its surroundings provide clues about how galaxies exchange material with the intergalactic medium. Its tidal tails, for example, may contribute gas and stars to nearby galaxies or serve as a reservoir of material for future interactions. This connectivity underscores the idea that no galaxy exists in isolation, each one is part of a larger cosmic ecosystem. The Medusa galaxy also challenges our understanding of time on a cosmic scale. While its current state appears static in human terms, it is merely a fleeting moment in its evolutionary journey. Over millions of years, the galaxy's tidal tails will dissipate, its starburst activity will wane, and its chaotic structure will settle into a more stable elliptical form. Observing the Medusa today is like catching a snapshot of a dynamic process that has been unfolding for billions of years and will continue long after our own existence. The celestial hydra is more than a scientific curiosity, it is a source of inspiration and wonder. Its breathtaking appearance, with its vivid hues and intricate patterns, reminds us of the universe's capacity for creating beauty out of chaos. For astronomers, it represents a treasure trove of knowledge, a place where they can study the forces that have shaped the cosmos. For the public, it is a symbol of the vastness and complexity of the universe, sparking curiosity and a sense of connection to the cosmos. As technology advances, the Medusa galaxy will remain a focal point for exploration and discovery. Future missions, such as those using the European Space Agency's Athena X-ray Observatory or next-generation radio telescopes, will uncover new details about this enigmatic system. These observations will deepen our understanding of everything from black hole physics to the large-scale structure of the universe. The Medusa, with its rich tapestry of phenomena, will continue to inspire new questions and drive the quest for answers, ensuring its place as one of the most scientifically valuable and awe-inspiring objects in the night sky. Through the Medusa galaxy, we are reminded of the universe's infinite complexity and its capacity for transformation. It is a living testament to the forces of change, a cosmic dance where destruction and creation are intertwined. As we continue to study this remarkable galaxy, we are not just learning about a distant object, we are uncovering the story of the universe itself, a story that includes our own origins and our place within the grand cosmic web. The Medusa galaxy stands as a cosmic stage where the grand forces of the universe play out their intricate roles. It is a living illustration of how galaxies evolve through time, shaped by the interplay of gravity, turbulence, and the relentless push and pull of interstellar material. What makes this system truly remarkable is its ability to combine these dramatic processes into a cohesive, albeit chaotic, masterpiece of science and art. One of the most captivating aspects of the Jellyfish galaxy is the sheer scale and energy of its starburst activity. Within its core lies a seething cauldron of star formation, where gas and dust collapse under intense gravitational forces to form clusters of massive stars. These stars, in turn, light up their surroundings with ultraviolet radiation, ionizing the gas and creating vast bubbles of glowing plasma. The winds and shock waves generated by these stars further compress nearby gas clouds, triggering a chain reaction of star formation. This feedback loop is a vital piece of the puzzle in understanding how galaxies sustain and regulate star formation over time. The tidal tails of the nebular serpent continue to offer insights into the aftermath of galactic collisions. These vast streams of stars and gas are essentially the cosmic fingerprints left behind by the gravitational interaction of the parent galaxies. They stretch outward into intergalactic space, carrying with them valuable clues about the Medusa's past. Embedded within these tails are small, dense regions where stars are still forming, providing a unique environment that contrasts sharply with the crowded, high-pressure starburst regions in the galaxy's core. These remote pockets of star formation allow astronomers to study how stars can arise in low-density regions, offering a new perspective on the diversity of star-forming conditions in the universe. The radiant chimera also provides a window into the complex interplay between its central supermassive black hole and its surrounding environment. The black hole, a voracious force at the heart of the galaxy, feeds on gas and dust pulled toward its event horizon. This process generates immense energy, which is released in the form of jets and outflows that ripple through the galaxy. These high-energy phenomena are not just destructive, they play a crucial role in shaping the galaxy's structure by redistributing gas, regulating star formation, and even enriching the intergalactic medium with heavy elements. The Medusa galaxy, therefore, is a prime example of how black holes influence not only their immediate surroundings but also the larger-scale evolution of their host galaxies. Another intriguing feature of the stellar hydra is the role of its dust and molecular clouds. Dust grains, though tiny on an individual scale, collectively act as the cosmic glue that binds together the ingredients for star formation. These grains absorb and scatter light, obscuring parts of the galaxy when viewed in optical wavelengths but glowing brightly in the infrared. Observing the Medusa in these longer wavelengths reveals a hidden world of activity, where dense molecular clouds are collapsing to form the next generation of stars. This ability to study the invisible aspects of the galaxy is a testament to the power of modern observational technology, which continues to peel back the layers of mystery surrounding systems like the Medusa. The Serpentine galaxy is also a case study in the chemical enrichment of the cosmos. The heavy elements forged in the cores of stars and released through supernova explosions are dispersed throughout the galaxy, enriching its gas and dust with the building blocks of planets and, potentially, life. Spectroscopic studies of the Medusa have revealed a rich tapestry of elements, including carbon, oxygen, and nitrogen, which are vital for the development of complex organic molecules. By tracing the distribution and abundance of these elements, astronomers can piece together the history of star formation and chemical evolution within the galaxy. On a larger scale, the Medusa galaxy serves as a microcosm for understanding the hierarchical nature of cosmic structure. Its collision and subsequent evolution are part of a broader narrative in which small systems merge to form larger ones, a process that has shaped the universe from its earliest days. The Medusa's current state, with its chaotic appearance and intense activity, offers a snapshot of this process in action, allowing astronomers to study the mechanisms that drive the growth of galaxies and the larger cosmic web. The chaotic beauty of the celestial hydra also has profound implications for the study of time in the universe. The tidal tails and starburst regions we observe today are the direct results of events that unfolded millions of years ago. Light from the Medusa takes 130 million years to reach us, meaning that we are witnessing the galaxy as it existed during the age of the dinosaurs on Earth. This temporal disconnect highlights the vast scales of time and space that define the universe, reminding us of our own fleeting moment in cosmic history. In addition to its scientific significance, the Medusa galaxy is a beacon of inspiration for humanity. Its vivid colors, intricate structures, and dynamic processes captivate the imagination, serving as a powerful reminder of the universe's boundless creativity. The galaxy's very existence challenges us to think beyond the confines of our own planet and to consider the larger forces at work in shaping the cosmos. It is a testament to the ingenuity of human exploration that we can study such distant and complex systems, uncovering their secrets and expanding our understanding of the universe. As we continue to probe deeper into the mysteries of the radiant Gorgon, new discoveries are certain to emerge. Upcoming missions and observatories, equipped with cutting-edge technology, promise to reveal even more about the galaxy's hidden features and the processes driving its evolution. From the faintest stars in its tidal tails to the energetic jets emanating from its central black hole, the Medusa galaxy remains a treasure trove of scientific opportunity, a cosmic jewel whose mysteries will keep astronomers enthralled for generations to come. The Medusa is a reminder that the universe is a place of constant change and transformation. Its story is one of destruction and creation, chaos and order, beauty and power. In studying this galaxy, we not only learn about its unique characteristics but also uncover universal truths about the forces that shape the cosmos. The Medusa galaxy, in all its complexity, is a testament to the resilience and interconnectedness of the universe, a timeless symbol of the eternal dance of the stars. The Medusa galaxy's dynamic nature ensures it remains a central focus in the study of galactic evolution. Its story is one of endless change, revealing the universe's capacity for both destruction and renewal. Each feature, from its luminous starburst core to its vast tidal tails, offers a piece of the puzzle, helping astronomers decode the mechanisms that have shaped galaxies across billions of years. The Medusa is not just a snapshot of cosmic evolution, it is a window into the processes that define the life cycles of galaxies, providing an unparalleled opportunity to study the forces at work in the cosmos. The ongoing star formation in the Jellyfish galaxy serves as a testament to the transformative power of galactic collisions. These processes compress interstellar gas to densities that ignite star formation on an extraordinary scale. The galaxy's central regions, where these processes are most intense, shine with the brilliance of countless young, massive stars. These stars burn hot and fast, emitting streams of radiation and powerful stellar winds that shape the surrounding environment. Their lifespans are brief in cosmic terms, often ending in supernova explosions that release heavy elements and energy into the interstellar medium. Each explosion enriches the galaxy, seeding the material necessary for the next generation of stars and planets. Meanwhile, the Medusa's tidal tails are not merely remnants of its violent past but active regions of transformation. These extended arms of stars and gas stretch across tens of thousands of light-years, containing clumps of material dense enough to form stars. In these distant outposts, removed from the central starburst, star formation proceeds at a more sedate pace, creating a striking contrast between the chaotic core and the serene outskirts. These regions also provide insight into how material expelled during collisions contributes to the broader galactic ecosystem, as these streams often interact with neighboring galaxies or feed into the intergalactic medium. One of the most intriguing aspects of the nebular Gorgon is its central supermassive black hole, a colossal entity that exerts a profound influence on the galaxy. The black hole's gravitational pull drives the accretion of surrounding gas and dust, generating immense amounts of energy as this material is heated to extreme temperatures. The resulting jets and outflows of energy ripple through the galaxy, shaping its structure and regulating star formation. These feedback mechanisms are a crucial component of galactic evolution, as they can suppress star formation by expelling gas or, conversely, trigger new starbursts by compressing gas in certain regions. The Medusa offers a rare opportunity to study these effects in detail, helping astronomers understand how black holes and galaxies co-evolve. The study of the stellar hydra's interstellar medium further deepens our understanding of the galaxy's complex processes. The collision that birthed the Medusa created a highly turbulent environment where gas exists in a variety of states, from cold molecular clouds to hot ionized regions. These different phases interact in complex ways, creating a dynamic medium where star formation and feedback processes constantly reshape the galaxy. Observations at different wavelengths, from radio to X-rays, allow astronomers to map these interactions and gain insight into the physical conditions that drive galactic evolution. The chemical richness of the Serpentine galaxy is another key area of study. The heavy elements dispersed by previous generations of stars are now a fundamental part of the galaxy's makeup, influencing everything from star formation to the development of planetary systems. By analyzing the spectra of light emitted by the galaxy, astronomers can trace the distribution and abundance of these elements, piecing together the history of chemical enrichment that has occurred over billions of years. This chemical legacy is not just a feature of the Medusa itself but a contribution to the cosmic ecosystem, as the galaxy's interactions with its surroundings disperse these elements into the intergalactic medium. The Medusa also offers a glimpse into the broader cosmic web, the vast network of galaxies, dark matter, and intergalactic gas that spans the universe. Its tidal tails and interactions with nearby galaxies are part of this larger structure, illustrating the interconnectedness of galaxies within clusters and superclusters. These interactions are not isolated events but part of a larger narrative in which galaxies grow and evolve through mergers and exchanges of material. The medusa's place within this web highlights the importance of understanding not just individual galaxies but their roles within the broader cosmic context. The celestial hydra's current state, though chaotic, is only a transitional phase in its long evolutionary journey. Over time, the intense starburst activity will subside as the available gas is consumed or expelled, and the galaxy will settle into a more stable configuration, likely taking on the elliptical shape typical of post-merger systems. This transformation offers a glimpse into the long-term effects of galactic collisions, providing a model for understanding the eventual fate of galaxies like our own Milky Way, which is destined to merge with the Andromeda Galaxy in a similar event. What makes the radiant chimera so captivating is not just its scientific significance but its ability to inspire wonder and curiosity. Its striking appearance, with vibrant colors and intricate structures, serves as a reminder of the universe's boundless creativity. For astronomers, it represents a treasure trove of data, a system where countless physical processes can be studied in detail. For the public, it is a symbol of the universe's majesty, sparking a sense of connection to the cosmos and a desire to explore its mysteries further. As technology advances, the Medusa galaxy will remain at the forefront of astronomical research. New telescopes and observatories, equipped with cutting-edge instruments, will allow us to probe deeper into this enigmatic system, uncovering hidden features and revealing new aspects of its nature. From its turbulent core to its serene outskirts, the Medusa promises to continue providing valuable insights into the forces that shape galaxies and the universe as a whole. The Medusa galaxy, in all its complexity, reminds us of the dynamic and ever-changing nature of the cosmos. It is a living testament to the universe's capacity for transformation, a place where destruction gives rise to creation and chaos leads to beauty. Through the study of this remarkable galaxy, we not only expand our understanding of the universe but also gain a deeper appreciation for the intricate processes that have shaped our own cosmic home. The Medusa is more than a galaxy, it is a cosmic masterpiece, a source of endless fascination, and a symbol of the universe's eternal dance of change. The Medusa Galaxy, or NGC 4194, offers an almost inexhaustible reservoir of phenomena to investigate, particularly in the realm of astrophysics. Its chaotic yet coherent structure is a rich tapestry woven from the interaction of gravitational forces, thermodynamics, and chemical processes. Each layer of its complexity reveals fundamental insights into the processes that shape galaxies throughout the cosmos. At its core, the Medusa Galaxy is a laboratory for understanding the intricate mechanisms governing galaxy formation, evolution, and interaction. A key area of scientific inquiry in the Medusa Galaxy is its molecular gas content, which serves as the primary fuel for star formation. Observations at submillimeter wavelengths, such as those conducted by instruments like ALMA, Atacama Large Millimeter/Submillimeter Array, have revealed vast reservoirs of cold molecular hydrogen, H2, concentrated in the central regions of the galaxy. These gas clouds, often containing traces of carbon monoxide, CO, that make them detectable, are subjected to intense gravitational compression during the merger process. The resulting high densities lead to efficient star formation, transforming these reservoirs into clusters of massive, short-lived stars. Studying the properties of molecular gas in the Medusa provides insight into how galactic collisions enhance star formation and how these processes compare to quiescent galaxies. The dynamics of the interstellar medium, ISM, in the Medusa galaxy are another focus of intense study. The collision has created an environment where turbulence dominates, with gas flowing in streams, eddies, and shocks. This turbulence plays a dual role. While it prevents some regions of the gas from collapsing into stars, it also compresses other regions, triggering star formation. Understanding how turbulence operates in such an extreme environment is critical for building models of star formation, as it bridges the gap between small-scale physics within molecular clouds and large-scale galactic dynamics. Beyond the ISM, the Medusa's starburst activity provides a wealth of data for understanding the interplay between newly formed stars and their environment. Massive stars emit intense ultraviolet radiation that ionizes nearby gas, creating regions of ionized hydrogen, H2 regions. These regions glow brightly in visible light, particularly in specific emission lines like H-alpha, which can be used to map the spatial distribution of star formation across the galaxy. Simultaneously, the winds from these stars, along with the eventual supernova explosions, inject energy into the surrounding medium, driving outflows of gas. These outflows, sometimes referred to as galactic winds, are critical for regulating star formation by removing gas from the central regions and enriching the surrounding intergalactic medium with metals. The Medusa's active galactic nucleus, AGN, adds yet another layer of complexity. Powered by accretion onto a supermassive black hole, the AGN emits radiation across the electromagnetic spectrum, from radio waves to X-rays. This activity can have profound effects on the galaxy, both locally and on larger scales. High-energy photons and relativistic particles from the AGN can heat and ionize gas, potentially suppressing star formation in the immediate vicinity. However, in some cases, AGN-driven outflows can compress gas clouds and trigger star formation at larger distances. This dual role of AGN feedback makes it a key area of research, particularly in systems like the Medusa where both AGN and starburst activity are present. The chemical enrichment of the Medusa galaxy is another scientific frontier. The heavy elements created in stars and dispersed through supernova explosions enrich the galaxy's interstellar medium, altering the composition of future generations of stars and planets. By analyzing the galaxy's spectral lines, astronomers can determine the abundance of elements like oxygen, carbon, nitrogen, and iron, which are key indicators of a galaxy's evolutionary state. These observations help build a timeline of star formation and chemical evolution, offering clues about the progenitor galaxies that collided to form the Medusa. The tidal features of the Medusa, particularly its extended tails of stars and gas, provide critical evidence of the galaxy's violent origins. These tidal tails are formed by gravitational forces during the collision, pulling material outward into intergalactic space. Detailed studies of these structures can reveal the masses and trajectories of the colliding galaxies, as well as the distribution of dark matter within the system. Additionally, the star clusters found within these tails represent a unique environment for studying star formation outside the dense environments of galactic cores. Another fascinating aspect of the Medusa galaxy is its multi-wavelength signature. Each wavelength probes a different physical process within the galaxy. For instance, radio observations trace cold molecular gas, infrared observations reveal warm dust heated by young stars, optical wavelengths highlight ionized gas and stellar populations, and X-rays capture the high-energy processes associated with the AGN and supernova remnants. Combining data from these wavelengths creates a comprehensive picture of the galaxy, allowing astronomers to study its various components in unprecedented detail. The Medusa's relevance extends beyond its individual characteristics to its role in the broader context of cosmic evolution. Galaxy mergers, such as the one that created the Medusa, are thought to play a significant role in the hierarchical growth of structure in the universe. By observing systems like the Medusa at different stages of their evolution, astronomers can piece together the sequence of events that leads to the formation of massive elliptical galaxies, the end state for many merging systems. These observations are also crucial for understanding the future evolution of our own Milky Way, which is expected to merge with the Andromeda Galaxy in several billion years. Moreover, the Medusa galaxy provides a valuable test case for numerical simulations of galaxy mergers. By comparing observations of the Medusa with the results of simulations, astronomers can refine their models, improving our understanding of the physical processes involved in such interactions. These simulations incorporate a wide range of phenomena, including gravity, hydrodynamics, star formation, feedback from stars and black holes, and the influence of dark matter. The Medusa's detailed observational data serve as a benchmark for testing these complex models, helping to bridge the gap between theoretical predictions and real-world observations. In summary, the Medusa galaxy is not just an object of astronomical beauty but a cornerstone for scientific discovery. Its unique combination of features, intense starburst activity, a turbulent interstellar medium, an active nucleus, and extended tidal structures, makes it a microcosm of the processes that shape galaxies throughout the universe. As technology continues to advance, enabling more detailed observations and sophisticated simulations, the Medusa will undoubtedly remain a focal point for research, offering new insights into the forces that drive the cosmos. Its story, one of chaos, transformation, and renewal, mirrors the larger narrative of the universe itself, a testament to the intricate and dynamic nature of the cosmos. The Medusa galaxy remains an unending source of scientific exploration, not only due to its present structure but also because of the insights it provides into the universal laws governing galaxies and their evolution. Its story is a cosmic narrative of gravity, turbulence, stellar feedback, and chemical enrichment that unfolds across multiple dimensions of time and space. Each element within this galactic system adds to our understanding of the mechanisms that build, sustain, and ultimately transform galaxies. One particularly compelling aspect of the Medusa is its role as a natural experiment in gravitational physics. Galactic collisions like the one that formed NGC 4194 occur under the influence of dark matter halos that envelop each galaxy. These halos, made of invisible and mysterious dark matter, govern the overall dynamics of the merger. By studying the motion of stars and gas within the Medusa, astronomers can indirectly map the distribution of dark matter and gain critical insights into its properties. For instance, the gravitational effects seen in the tidal tails and the overall kinematics of the system provide evidence of how dark matter influences galaxy formation and interaction on both local and cosmic scales. The tidal structures of the Medusa are also prime sites for studying gravitational instabilities. The collision has stretched and redistributed material across enormous distances, creating localized regions of enhanced density where star formation has been triggered. These clumps, often referred to as tidal dwarf galaxies or protogalaxies, are fascinating laboratories for understanding how gravitational forces can condense material into new structures. Unlike their parent galaxies, these smaller systems are often dominated by recently formed stars and contain relatively little dark matter, challenging traditional models of galaxy formation. Beyond its gravitational dynamics, the Medusa galaxy is a hotbed of hydrodynamic processes. The merger has created an environment where interstellar gas flows are compressed, shock-heated, and rapidly mixed. These processes are best studied through high-resolution hydrodynamic simulations, which can replicate the chaotic flows observed in the Medusa. Shock fronts, in particular, play a critical role in triggering star formation by compressing gas into dense, star-forming filaments. By comparing simulations with observations, astronomers can refine their models of how shock waves and turbulence influence star formation, not just in mergers but in galaxies across the universe. The Medusa also offers a unique perspective on the life cycle of dust, an often overlooked yet vital component of galaxies. Dust grains, formed in the atmospheres of dying stars and supernovae, play a crucial role in cooling interstellar gas and enabling star formation. However, the extreme conditions in the Medusa, including powerful stellar winds, radiation pressure, and supernova shocks, subject dust to destruction and recycling processes. Infrared observations reveal how dust survives, evolves, and interacts with its environment in such harsh conditions. These studies are essential for understanding how dust contributes to the chemical and thermal balance of the interstellar medium. On larger scales, the Medusa galaxy exemplifies the role of feedback in regulating star formation. Feedback processes, driven by both stars and the central supermassive black hole, inject energy and momentum into the surrounding gas, creating outflows that can escape the galaxy's gravitational pull. These galactic winds carry metals into the intergalactic medium, enriching it with heavy elements that are crucial for the next generation of stars and planets. Observations of these outflows in the Medusa, particularly at X-ray and ultraviolet wavelengths, reveal their structure, composition, and impact on the galaxy's evolution. By studying the energy budget and efficiency of these processes, astronomers gain insights into how galaxies self-regulate their growth and star-forming activity. The Medusa's supermassive black hole, a dominant force in its central regions, further complicates the feedback picture. High-energy emissions from the black hole are thought to influence gas dynamics on scales ranging from a few light-years to tens of thousands of light-years. These emissions, often in the form of relativistic jets or ionized gas outflows, interact with the galaxy's interstellar medium in complex ways. In some cases, the energy released by the black hole heats the gas, preventing it from collapsing into stars, a phenomenon known as quenching. In others, the outflows compress gas clouds, triggering star formation at the edges of expanding shock fronts. The Medusa's combination of AGN activity and intense starburst regions provides a rare opportunity to study how these competing processes interact in real time. A particularly fascinating area of ongoing research involves the Medusa's role in the cosmic baryon cycle. Galaxies do not exist in isolation but are deeply interconnected with their surrounding environment through the exchange of gas and energy. The tidal tails and outflows of the Medusa contribute material to the intergalactic medium, while inflows of gas from the surrounding cosmic web replenish its star-forming reservoirs. This continuous exchange is a fundamental part of galaxy evolution, influencing everything from star formation rates to the growth of dark matter halos. Observing these exchanges in the Medusa provides a window into how galaxies maintain their activity over billions of years. The Medusa's importance is magnified when considered in the context of its potential future. The galaxy is currently in a transitional phase, evolving from the chaotic aftermath of its merger toward a more stable state. Over time, its intense starburst activity will diminish as its gas reservoirs are depleted or expelled. Eventually, the galaxy will settle into a quiescent elliptical form, dominated by older stars and lacking the dramatic features of its current state. This evolution mirrors the fate of many merging galaxies, offering a glimpse into the long-term processes that shape the universe's population of galaxies. From a cosmological perspective, the Medusa galaxy provides critical evidence for the hierarchical nature of galaxy formation. Its chaotic structure, active star formation, and tidal features are hallmarks of the processes that build larger structures from smaller components. These processes were even more common in the early universe, where galaxies were smaller and interactions more frequent. By studying the Medusa, astronomers can draw direct parallels to the conditions that shaped the first galaxies, bridging the gap between the ancient past and the present-day universe. As observational technology advances, the Medusa galaxy will continue to serve as a focal point for scientific discovery. Upcoming missions like the Square Kilometre Array, SKA, will enable detailed studies of its neutral hydrogen gas, mapping the large-scale flows that drive its evolution. Similarly, next-generation space telescopes such as the James Webb Space Telescope, JWST, and the planned Louvre Observatory will probe the Medusa's star-forming regions and AGN activity with unprecedented resolution and sensitivity. These observations will not only enhance our understanding of the Medusa itself but also refine our models of galaxy formation and evolution across the cosmos. Ultimately, the Medusa galaxy is far more than a cosmic curiosity, it is a cornerstone for understanding the universe. Its dynamic interplay of forces, from gravitational interactions to stellar feedback, encapsulates the complexity of the cosmos in a single system. By studying this remarkable galaxy, we uncover the universal principles that govern all galaxies, shedding light on the processes that have shaped the universe from its earliest moments to the present day. The Medusa is a testament to the beauty, complexity, and interconnectedness of the cosmos, a vivid reminder that even in chaos, the universe creates order and wonder. The Medusa galaxy continues to be a cornerstone of astrophysical research, offering profound insights into the processes that drive galaxy evolution. Its turbulent nature serves as a microcosm of universal phenomena, where the interplay between gravity, star formation, and feedback mechanisms unfolds on scales spanning light-years to tens of thousands of light-years. Scientists view the medusa as a dynamic laboratory for testing theories about galactic mergers, stellar birth and death, and the enrichment of the cosmos with heavy elements. A pivotal area of exploration in the Medusa galaxy is its interstellar medium, ISM, which has been violently reshaped by the collision that created it. The ISM in the Medusa exists in multiple phases: cold molecular gas, warm atomic gas, and hot ionized gas. These phases interact dynamically, exchanging energy and momentum through processes such as shock compression, turbulence, and radiative cooling. The collision has amplified these interactions, creating regions of intense star formation in areas where gas is stripped away, leaving voids. This highly disturbed ISM allows astronomers to study how energy and matter flow through galaxies and how these flows influence the life cycle of stars. One key feature of the Medusa's ISM is its reservoirs of cold molecular gas, which serve as the raw material for star formation. Observations with radio telescopes, such as ALMA, have detected vast clouds of molecular hydrogen, H2, concentrated in the central regions of the galaxy. These clouds are often traced using carbon monoxide, CO, emissions, which act as a proxy for the presence of molecular hydrogen. The extreme pressures and densities in these regions have triggered bursts of star formation, resulting in the formation of massive star clusters. Understanding how these dense molecular clouds collapse to form stars in such a chaotic environment provides vital clues about the conditions required for star formation, both in merging galaxies and in the broader universe. The Medusa galaxy's starburst regions, particularly in its core, are among the most luminous and active in the local universe. These regions are powered by the rapid formation of massive stars, which emit intense ultraviolet radiation that ionizes the surrounding gas. This ionized gas forms glowing regions known as H2 regions, which are key tracers of star formation activity. The size, luminosity, and distribution of these regions in the Medusa provide a detailed map of where star formation is most active and how it correlates with the dynamics of the galaxy. By studying the physical properties of these H2 regions, astronomers can better understand how the star formation rate is regulated in extreme environments. The stellar feedback from the newly formed stars in the Medusa is another area of active investigation. Massive stars have relatively short lifespans, often ending in spectacular supernova explosions that release vast amounts of energy into the surrounding medium. These explosions generate shock waves that compress nearby gas, potentially triggering new waves of star formation. At the same time, the energy released can heat and disperse gas, reducing the efficiency of future star formation. Observations of the Medusa have revealed evidence of both processes occurring simultaneously, providing a unique opportunity to study how stellar feedback shapes the evolution of galaxies. The Medusa's active galactic nucleus, AGN, adds another layer of complexity to this already dynamic system. Powered by a supermassive black hole at the galaxy's center, the AGN emits energy across the electromagnetic spectrum, from radio waves to X-rays. This energy output is driven by the accretion of gas onto the black hole, which forms a hot, rotating disk around it. The AGN's powerful radiation and relativistic jets interact with the surrounding ISM, heating gas and driving large-scale outflows. These outflows, often referred to as galactic winds, can have profound effects on the galaxy's evolution by removing gas that would otherwise fuel star formation. The Medusa's AGN provides a critical case study for understanding how these feedback mechanisms operate in galaxies experiencing simultaneous AGN activity and starbursts. Another fascinating aspect of the Medusa galaxy is its chemical evolution. The heavy elements, or metals, present in the galaxy are the products of nucleosynthesis in stars. When stars die, particularly in supernova explosions, they release these metals into the ISM, enriching it with elements like oxygen, carbon, and iron. Observations of the Medusa have revealed high metallicities in its central regions, consistent with the intense star formation and supernova activity occurring there. By studying the distribution of metals in the Medusa, astronomers can trace the processes that have enriched the galaxy over time and compare them to those in other merging systems. The tidal tails of the Medusa galaxy are another focus of scientific attention. These long, sweeping structures are composed of stars, gas, and dust that were gravitationally stripped from the galaxy during the merger. Tidal tails are rich with clues about the history of the interaction, including the masses and orbital dynamics of the progenitor galaxies. Embedded within these tails are dense clumps of gas and young stars, some of which may evolve into independent systems, known as tidal dwarf galaxies. These structures are valuable for studying star formation in low-density environments and for understanding the role of tidal interactions in galaxy evolution. From a cosmological perspective, the Medusa galaxy is a window into the processes that shaped the early universe. In the first few billion years after the Big Bang, galaxy mergers were far more common, as galaxies were smaller and more densely packed. The Medusa's chaotic state, intense star formation, and active nucleus mirror the conditions that would have been typical in this era. By studying the Medusa, astronomers can draw parallels to the formation of the first galaxies, shedding light on how the universe evolved from a chaotic, primordial state to the structured cosmos we see today. The Medusa galaxy also plays a role in the broader cosmic ecosystem. Its tidal tails and galactic winds contribute material to the intergalactic medium, IGM, enriching it with metals and energy. This material can later be accreted by other galaxies, continuing the cycle of enrichment and evolution. Observing how the Medusa exchanges matter and energy with its surroundings provides valuable insights into the interconnected nature of galaxies and the larger cosmic web. Future observations of the Medusa galaxy promise to unlock even more of its secrets. Instruments like the James Webb Space Telescope, JWST, and next-generation ground-based observatories will provide unprecedented views of the galaxy's core, tidal structures, and star-forming regions. These observations will reveal the physical processes driving the Medusa's evolution with unprecedented clarity, offering new opportunities to test theories about galaxy formation and interaction. In conclusion, the Medusa galaxy is far more than a visual marvel. It is a scientific treasure trove that encapsulates the fundamental processes shaping galaxies across the cosmos. Its chaotic yet beautiful structure serves as a living laboratory for exploring the laws of physics, the life cycles of stars, and the evolution of the universe itself. As we continue to study the Medusa, we not only deepen our understanding of this remarkable galaxy but also uncover the universal principles that govern the cosmos, connecting us to the grand narrative of creation and transformation that defines the universe. The Medusa galaxy, with its turbulent and transformative nature, remains a profound example of the cosmos' relentless capacity for change and adaptation. As astronomers delve deeper into its structure, the galaxy reveals a multitude of complex processes operating on every conceivable scale, from the microscopic interactions of particles in the interstellar medium to the grand dynamical movements of entire stellar populations. Each layer of the Medusa's anatomy presents opportunities to explore the physics that govern not only its own evolution but the evolution of galaxies throughout the universe. One of the central themes in studying the Medusa galaxy is understanding the physics of shock waves generated by its galactic collision. These shock waves, which propagate through the interstellar medium at supersonic speeds, play a critical role in heating and compressing gas clouds. Observations in X-ray and radio wavelengths reveal the presence of these shock fronts, which often light up in emission lines characteristic of ionized gases. By analyzing these emissions, astronomers can determine the temperature, density, and velocity of the shocked gas, offering insights into the energy dissipation mechanisms at work. This knowledge is vital for understanding how such violent events can both trigger and inhibit star formation, depending on local conditions. In addition to shocks, the turbulent nature of the Medusa's ISM provides a unique opportunity to study turbulence in astrophysical plasmas. Turbulence within galaxies is thought to cascade energy from large to small scales, creating intricate structures within molecular clouds. These turbulent motions contribute to the fragmentation of gas clouds, which ultimately leads to the formation of stars. The medusa's highly disturbed environment amplifies these processes, making it an ideal testbed for studying the transition from large-scale galactic dynamics to small-scale star-forming cores. Numerical simulations, combined with multi-wavelength observations, help astronomers model these turbulent flows, providing a deeper understanding of how turbulence shapes the life cycle of galaxies. Another fascinating aspect of the Medusa galaxy is the role of magnetic fields in its evolution. While often overlooked, magnetic fields can influence the dynamics of gas and dust within galaxies. Observations using radiopolarimetry can detect synchrotron radiation emitted by relativistic electrons spiraling around magnetic field lines, revealing the structure and strength of these fields. In the Medusa, magnetic fields may play a role in channeling gas flows, aligning dust grains, and even affecting the propagation of cosmic rays. Understanding these effects is crucial for developing a comprehensive picture of how galaxies like the Medusa evolve over time. The Medusa's starburst regions also provide a laboratory for studying feedback from massive stars. These stars, often grouped into massive star clusters, generate intense stellar winds and ultraviolet radiation fields that shape their surroundings. The energy injected by these feedback processes can drive large-scale galactic outflows, contributing to the regulation of star formation and the enrichment of the intergalactic medium. These outflows, observed as expanding bubbles and shells in the Medusa, carry information about the energy output of the starburst and the efficiency of feedback mechanisms. Measuring the kinematics and composition of these outflows allows astronomers to quantify the impact of stellar feedback on galaxy evolution. Furthermore, the Medusa's central active galactic nucleus, AGN, offers a rare chance to study the coevolution of supermassive black holes and their host galaxies. The AGN's powerful radiation not only affects the surrounding gas but also interacts with the galaxy's magnetic fields, influencing the morphology and dynamics of the ISM. High-resolution spectroscopy across various wavelengths, ranging from optical to X-ray, allows astronomers to dissect the AGN's emission mechanisms, revealing the accretion processes at work. By understanding how the AGN influences its host galaxy, scientists can better comprehend the symbiotic relationship between black hole growth and galactic evolution. The chemical evolution of the Medusa galaxy is also a critical area of study. The intense star formation activity enriches the ISM with heavy elements, or metals, which are synthesized in the cores of stars and dispersed through supernova explosions. Detailed spectroscopic analyses reveal the abundance gradients of these elements across the galaxy, providing a timeline of chemical enrichment. This, in turn, informs models of star formation efficiency and the initial mass function, IMF, within starburst galaxies. By comparing these observations with theoretical models, astronomers can trace the pathways through which galaxies like the Medusa evolve chemically over billions of years. Another intriguing phenomenon observed in the Medusa is the presence of high-velocity clouds, HVCs, which are massive blobs of gas moving at velocities significantly different from the galaxy's disk rotation. These HVCs may represent infalling material from the cosmic web, contributing fresh gas that sustains star formation, or they might be remnants of past galactic interactions. Studying these clouds can provide insights into the processes of galactic accretion and recycling, critical for understanding long-term galaxy evolution. On a cosmological scale, the Medusa galaxy serves as a snapshot of a pivotal stage in galaxy evolution. It exemplifies how galactic mergers contribute to the hierarchical assembly of structure in the universe. By observing the Medusa, astronomers gain a better understanding of how small protogalaxies merge and coalesce into the massive galaxies observed today. The Medusa's current chaotic state mirrors the conditions of the early universe when galaxy mergers were more frequent, thus offering a rare glimpse into the past epochs of cosmic evolution. Future observations with upcoming facilities like the 30-meter telescope, TMT, and the European Extremely Large Telescope, EELT, will allow astronomers to resolve even finer details within the Medusa. Adaptive optics systems will provide sharper images of its star-forming regions and AGN, while advanced spectrographs will dissect its chemical composition and kinematics with unprecedented precision. These observations will enable a more detailed understanding of the physical processes driving the medusa's evolution. In addition, simulations using next-generation supercomputers will model the complex interactions observed in the medusa. These simulations incorporate not only gravitational dynamics but also hydrodynamics, magnetohydrodynamics, and radiative transfer, offering a multi-scale, multi-physics approach to galaxy evolution. By comparing these models with observational data, astronomers can refine their theories of galaxy formation and feedback mechanisms, bridging the gap between theoretical predictions and empirical observations. In summary, the Medusa galaxy is a dynamic and evolving system that encapsulates the myriad processes governing galaxy evolution. Its rich tapestry of interactions, from stellar feedback to AGN activity and chemical enrichment, provides a comprehensive view of the forces that shape galaxies. As technology advances, the Medusa will remain a cornerstone for astrophysical research, continually revealing the intricate and interconnected nature of the universe. Through its study, we not only unlock the secrets of a single galaxy but also gain profound insights into the workings of the cosmos itself, a testament to the enduring power of scientific exploration. The Medusa galaxy, in all its chaos and complexity, is a profound testament to the dynamism of the cosmos. It stands as a living reminder that the universe is a place of constant motion, transformation, and interplay between destruction and creation. The Medusa is not merely a product of its past, a violent collision that birthed its tumultuous features, but also a harbinger of its future, one that encapsulates the life cycle of galaxies on both micro and macro scales. Its central starburst regions, ignited by the compression of gas during the merger, represent the raw power of gravitational interactions. Here, the seeds of new stars are planted in the wake of cosmic violence, shining as beacons of renewal. These young stars live brief but brilliant lives, enriching the surrounding medium with heavy elements when they die in supernova explosions. This cycle of birth, life, and death plays out on a galactic scale, weaving the intricate tapestry of the Medusa's evolving structure. Each generation of stars contributes to the enrichment of the interstellar medium, laying the foundation for the future development of stars, planets, and, potentially, the conditions necessary for life. The tidal tails of the Medusa stretch out like cosmic arms, connecting the galaxy to its broader environment and to its past. These tails, composed of stars and gas pulled away by tidal forces, tell the story of the violent merger that shaped the galaxy. They are not merely remnants of destruction but zones of ongoing creation, where star clusters form in the low-density outskirts, unbound by the constraints of the galactic core. These features serve as a bridge between the Medusa and the intergalactic medium, facilitating the exchange of material that drives the larger cosmic cycle of matter and energy. At the heart of the Medusa, the supermassive black hole exerts its immense influence, anchoring the galaxy while simultaneously shaping its fate. The active galactic nucleus, AGN, fueled by the accretion of matter, sends out jets of energy that ripple through the interstellar medium, regulating star formation and driving galactic winds. This dual role of creation and destruction highlights the intricate balance of forces that govern the galaxy's evolution. The AGN's feedback mechanisms demonstrate how supermassive black holes and their host galaxies are fundamentally linked, influencing each other in profound ways that shape their destinies over billions of years. The Medusa is not only a snapshot of its own life cycle but also a window into the broader history of the universe. Its features mirror the conditions of the early cosmos, where galaxy mergers and interactions were far more frequent. By studying the Medusa, astronomers gain a better understanding of how the first galaxies formed and evolved in a turbulent environment, paving the way for the structured universe we observe today. The galaxy's current chaotic state offers a glimpse into the processes that were once commonplace, revealing the mechanisms that shaped the cosmic web and the large-scale structure of the universe. As the Medusa continues its transformation, it will ultimately settle into a more stable configuration, likely becoming an elliptical galaxy. The starburst activity will fade as its gas reservoirs are depleted, and its once chaotic features will give way to a more uniform structure. This evolution is part of the natural life cycle of galaxies, a process that plays out over billions of years. Observing the medusa in this transitional phase provides an invaluable opportunity to study these transformations in real time, offering insights into the long-term evolution of galaxies like our own Milky Way. The Medusa galaxy also connects us to the future of our cosmic neighborhood. Our Milky Way is on a collision course with the Andromeda galaxy, a merger that will occur in approximately 4.5 billion years. When this happens, the resulting structure will resemble the Medusa galaxy, with tidal tails, intense starburst activity, and a central supermassive black hole shaping its destiny. By studying the Medusa, we gain not only a glimpse into the distant past but also a preview of the cosmic events that await us. On a larger scale, the Medusa galaxy is a vivid reminder of the interconnectedness of the universe. Its interactions with neighboring galaxies, its exchange of matter with the intergalactic medium, and its role in enriching the cosmic web illustrate that no galaxy exists in isolation. The processes observed in the Medusa are not unique to it but are part of the universal forces that shape all galaxies, including our own. Through the Medusa, we see the threads that connect every galaxy in the cosmos, forming a vast and intricate network of matter, energy, and gravity. As observational technology continues to advance, the Medusa galaxy will remain a cornerstone for astrophysical research. Next-generation telescopes and instruments, from the James Webb Space Telescope to the Extremely Large Telescope, will enable astronomers to probe deeper into its structure, unraveling the physical processes that drive its evolution. High-resolution imaging, spectroscopy, and simulations will allow scientists to explore the Medusa at unprecedented levels of detail, uncovering the secrets of its starburst regions, AGN, tidal tails, and interstellar medium. These discoveries will not only enhance our understanding of the Medusa but also refine our knowledge of galaxy evolution across the universe. Ultimately, the Medusa galaxy is far more than a single object in the night sky. It is a cosmic masterpiece, a symbol of the universe's endless creativity, and a reminder of the intricate forces that govern the cosmos. Its chaotic beauty reflects the dynamic nature of the universe, where destruction leads to creation, and chaos gives rise to order. By studying the Medusa, we are not just exploring a distant galaxy, we are uncovering the fundamental principles that shape the cosmos itself. The Medusa invites us to reflect on our place in the universe. Its story of transformation and interconnectedness echoes our own, reminding us that we are part of the same cosmic fabric. From the heavy elements forged in its stars to the energy exchanged in its interactions, the processes that define the Medusa are the same ones that made life on Earth possible. In this sense, the Medusa galaxy is not just a subject of scientific inquiry but a profound source of inspiration, connecting us to the vast and ever-changing universe we call home.